Hey, Professor.
Hey, how's it going, Micah?
Doing well. Just a quick question.
No problem.
I know you sent us an announcement that the test would be pushed back to the 17th, and it says down the syllabus as well, right? Uh,
Uh, gotcha. So, yeah, it's you're actually allowed any day this week to get it done.
okay. Because I noticed the due date on Canvas, it says the 21st.
Yeah. So what I did was, I think I even made it available for next for Monday. In other words,
Uh,
a week from yesterday, just in case anybody had any difficulty since I pushed it back. So you, in principle, could even take it Monday. I might have to pull some strings to get you to open that because when I originally put it in, I put it in through the Sunday, which is the 20th. But if you want to go on the 21st, I can just let them know and they'll take it.
okay. Okay. Um, and how does the camera situation work again? Like, is that going to be through Respondus webcam
Oh,
or
no, this is you're supposed to take it by a proctor. So like if you can get to any of the TCC campuses, they can do it. If you're not anywhere near a TCC campus, then you might have to pay someone to proctor it.
okay? Because I remember you mentioning about like a mirror through the
Yeah,
webcam situation.
that's that's a way that I can do it if there's no other way, but I do try to avoid that just because of the hassle. But if that's something that you're going to need, I could probably figure out a way to help you with that.
Okay, I'll let you know. If I do need it, I'll email you before the weekend.
Yeah.
Okay.
Normally, when we do that, it would be a Respondus lockdown browser as well as Respondus monitor, and
Mhm.
then you have at least like a 8 by 10 type mirror where you can sort of sit at an angle, and the mirror allows me looking through the camera of the monitor, whatever kind of camera you have, allows me to look into that mirror and see what's going on with your desktop, your hands, that sort of thing. Uh,
Okay.
it's mainly because I get a lot of people doing like this, and you you can usually figure out what that is.
Yeah, because like I did have like a mirror and everything prepared that, could show everything around my
So
workspace
if
situation.
you can't make it, if you can't figure out a way to make it to one of the campuses, just let me know, and we'll work out a day. And either you can do it on your own at that time, or I might even be able to proctor it for you at some time.
Okay, sounds good.
All right, Danielle, do you have a question?
Yeah, I also had a question on it. So I won't have time to go into a campus, but I go to Virginia Wesleyan, so I was wondering if like one of my professors could proctor it.
Yeah, they can do that. Virginia Wesleyan might have a testing center as well that can do it. If yeah, any of those nearby schools will be fine.
Okay, I'll just take it at my testing center then. Would I still need to record like what I'm doing and everything?
No, but whoever is doing it at the testing center, they should have a procedure that's required. And if they don't, I have some questions that I can send them a form that basically just says what I expect. So we've got to communicate one way or the other for that for you to do it.
I will also probably have to take it Monday because my week is also pretty slammed.
Okay. That's not a big deal. Like I said, we can set it up Monday, and it won't even be a problem if you're going to take it not at one of our campuses. I don't even have to give them a heads up on that because I'm just going to a different place.
Okay, thank you so much.
No problem. You're welcome. Anybody else have a question? All right. Let me check my. I was in the process of getting my notebook ready. It looks like I did. Today's the 15th, right? Yes, I did. Okay. So I got all that. Ooh, another person. Oh, my students are getting here early. Rock on. Well, half a minute early. All right. Any other questions before we get started, folks? Because I'm getting ready to open up a can to scare you.
I'm sorry if you already went over this. I just wanted to, I know you had said potentially we could do the respondus with the mirror, but is that completely out for this test or is,
I'm trying to avoid that unless it's an absolute essential necessity. I'd prefer you to be able to do it on the campus, but if not, then there's a way we can do it. But
okay.
sort of get one chance. If something goes wrong, we're not going to be able to do it that way. But yeah, I can still work it out for if anybody really needs it.
Okay, thank you.
No problem, Carter. All right. So when we last met, I started to hint at talking about getting some examples of Gauss's law, and I need to go ahead and start off with the definition of electric flux. So there's this quantity called electric flux that turns out is very valuable. Not only that, electric flux as well as magnetic flux turn out to be very valuable / important. So I've come up with a way of you thinking about it in hopes that you'll, in some sense, better understand what the flux is. So what I'm going to tell you is I'm going to go ahead and share my screen with you guys. And then I'm going to write out what the flux is in equation form. And I'm going to try to give you an example of it as well. So when we actually talk about flux, there's an electric flux and there's a magnetic flux. And it's usually indicated by the Greek letter capital Phi, P-H-I, okay? And we do this for the electric, or we do this for the magnetic. So this is electric and magnetic flux. So what I think is a good example or a good way of thinking about this is the following. So what I'm going to do is I'm going to imagine sort of a hole in a floor like this. Okay, and let's say this floor, this hole in the floor is 3.00 meters by 2.00 meters. And that the floor itself is actually not very thick. So it's sort of like a, 2-inch thick cement floor. So it doesn't have much of a side that you have to worry about hitting if you were trying to throw something through this hole like so. But what we're going to do is we're going to imagine that directly below it doing a great deal of work, but in fact a good ways below it, we're going to have an exactly the same size dump truck that is actually parked directly below this hole. Okay, so the dump truck bed is exactly the same size as the hole, and we've aligned it so that it's exactly under. So if we followed this little line down, it would run right into this corner. This one would run right into this corner. This one would run right into this corner, but that's not like a hallway or anything. We're just looking at a floor up here where the blue is. That's a floor like on the second or third floor. And then you go down a long ways below that hole, some maybe 30 feet, and is going to be an opening to a dump truck. So this is going to be the bed of our dump truck. So you can imagine the tires might look like this, something like that. And of course, the truck would obviously have a hood and all that good stuff as well, and would have front wheels somewhere along there. So we're just trying to picture a dump truck. And now what we're thinking about all of this is we're imagining throwing trash through this hole with the hopes of keeping track of exactly how much trash went into the dump truck bed. And just so it's looks more like a bed, let's put it that way. So you could imagine that when you throw trash, it might come in like this with a velocity pointing this way, and then another piece of trash might come in with a velocity this way, and so on and so forth. Now, if the velocity has any component to the left or to the right instead of straight down through this hole, because that gap is so large, so this is on the order of, let's say, 15 meters from here to here. If it has hardly any velocity whatsoever in the left-right direction or the forward-backward direction, then the actual trash is going to miss the bed of the truck. So what we look for is some way of keeping track of all the actual velocities, all the individual particles whose velocities were actually exactly perpendicular to this hole. In other words, they were shooting straight down. Because if they're shooting at some angle, they could actually miss the truck. And we might want to figure out a way to keep track of how many of those are doing that, because they don't have 100% probability of missing, but they have a high percentage. So if we could just adjust the number that you get of the objects that actually fall through the hole, if you could adjust that number to the number that's most likely to get through the hole, that would be kind of helpful. So what we can do is we can imagine representing this area as a single vector. And this area vector will be called A, and its magnitude is 2.00 meters times 3.00 meters. And it points, let's say, in the negative k hat direction. In other words, I'm going to say that vertical is the actual z direction, and this is pointing downward. So this is going to be negative 6.00 square meters in the k hat direction. Okay. So that's one way we could represent this vector, or represent this hole in the ground. The hole in the ground has an area vector that represents it. Now, there's a slew of vectors you could maybe choose to represent the hole. For instance, you could make a vector parallel to the 2 meter side, or a vector parallel to the 2 meter side closest to us. You could make one parallel to the 3 meter side on the right, or the 3 meter side on the left. And in fact, every angle between being parallel to that left side, being parallel to that bottom side, being parallel to that right side, or being parallel to that top side, every one of those angles in between all those could also be angles. You can't really make a good argument for why you would use, let's say, one parallel to the top 2.00 meters. Then there's no better reason for us to use that particular vector than there is to use the 3.00 meters on the left. But if we choose a direction that's perpendicular to it, then we've reduced it down to two choices. We've got a choice that points down. We've got a choice that points up. So ultimately, what we have done is we've chosen to represent an area by a vector whose length is equal to the area and whose direction is perpendicular to the actual surface that would be spanned by that, say, hole or whatever. So if you imagine laying, for instance, a tarp over the hole, then you have a surface over that hole, and then you imagine pulling it nice and tight and choosing a vector exactly perpendicular to that tarp. That would be the area vector. Okay, so we have two choices, up and down, and there's really not a good reason to choose one or the other. I just happen to choose down because we're pretending to be throwing stuff through this hole in hopes of it landing in the dump truck at the bottom. Okay, so I just chose it for this particular time, but I could have equally chosen it pointing up. Now, later, we will define what's called a Gaussian surface, and that will be a closed surface. So it'll have a clear inside and outside. Like, for instance, if you imagine stripping down to its simplest shape, the shape of a Pepsi can. So take out all those special little curves and the little dent in the bottom and just make it a regular cylinder that's hollow. So it'd be a nice flat circular disc on top. It'd be a nice flat cylindrical side, and then a nice flat circular disc on the bottom. That would be a closed surface as well, because you could put something in between the top surface and the bottom surface and the side surface, and that would be inside. And the only way you could move that something to the outside is by crossing one of those sides. So that's clearly a closed surface. A sphere, would have a clear inside and outside. And stuff like that. So when we actually have closed surfaces, then we can arbitrarily say, okay, we're going to choose to represent our area vectors as vectors that point from the inside out. And that's what we're ultimately going to do. But right now, when we're not doing a closed surface, we're arbitrary, either up or down. I'm going to say down. Now, what you're imagining doing is wanting to keep account of how many pieces of trash would actually land in the dump truck. So how many of the pieces of trash make it into the dump truck? So what you could imagine is creating a sensor that could detect individual particles and immediately figure out what their velocity vector is. So design an electronic system that can locate flying trash and determine its velocity vector. Okay. So we're imagining this device. You can sort of think of it as like a radar gun. You would need a radar gun, let's say, pointing parallel to the 3 meter side, and then another one pointing parallel to the 2 meter side, and then another one pointing up or down. The main thing is having 3 different dimensions, especially if they're perpendicular, makes it really easy to figure out what the x component, y component, and z component of the velocity would be. So you could literally just have a radar gun of some sort, or 3 different radar guns of some sort that could pick out those 3 components, and then just have a CPU that could rapidly do the calculation, and boom, you'd have a velocity vector. Then the electronic gadget will compute V dot A. Okay. Now remember, V dot A is the magnitude of V times the magnitude of A times the cosine of the angle between them. Now, what does that mean? Well, that means if this is your vector V, say, and this is your vector A, say, they're tail to tail, then this is the angle theta. And what you see from that is I can imagine this being a component of V. This is the component of V that is perpendicular to A. And then this one right here, I should put an arrow on that one too. This one is a component of V parallel to A. You notice that I'm using the perpendicular symbol for perpendicular, like it looks like upside down T, and then I'm using 2 parallel lines to represent parallel. Now, does everybody see what I mean by the V parallel to A? If you look at that, I think you will agree that V parallel to A, meaning the length of it, is actually going to be equal to just V times the cosine theta, which, by the way, is V cosine theta is right there in the dot product. All right. So this is why we as physicists and other sciences and engineering as well, this is what we often use our dot products for. Dot products allow you to find how much of one vector is parallel to another vector. In other words, if I just wanted to know what fraction of the velocity is parallel to the A, then I just take V dot A and divide out the A. Because V dot A gives me V times A times cosine theta, and I just want V cosine theta, right? So that's what we're sort of using here. Now, notice if it's 90 degrees, if V is completely perpendicular to A, we're going to get 0. So it completely cuts out any of the perpendicular components and only gives us back a fraction of the product of the two vectors, magnitudes, if the angle is not exactly 0. So you can sort of think of that as, well, that's good, because if I have a small parallel component, then the dot product will give me a very small number. And that would be consistent with a very small probability of that particular one landing in the dump truck. Whereas if you had a large parallel component, that would mean V dot A would be very close to the magnitude of V times the magnitude of A. And therefore you'd expect every one of those, or very close to every one of those pieces of trash, to make it in the dump truck. So by coming up with this, we found a way that we could electronically keep some count of exactly how many particles go through the hole and end up in the truck, as opposed to missing the truck. Does that make sense to everyone? It's a kind of far-fetched thing, because there's not really that much need for it. But lo and behold, having some knowledge of exactly what parts of the velocities are parallel to the A vector is super helpful. And in fact, what we could do, because the surface isn't always going to be nice and flat like this one, the surface can be quite curved. And if it's quite curved, then you've got a problem where the velocity vector would be different at each particular spot in the curved space. So if that's the case, what you want to do is dice up that surface into smaller and smaller rectangles, or whatever shapes you want to, and keep making them smaller and smaller until they're so small that the entire velocities that you could possibly get in all those little points within the chosen rectangle, all of those velocity vectors are the same, then you've gotten it small enough. Okay. And then you can also probably, because it's so small of a rectangle that you've chosen, there's probably just one vector that really matches perpendicular to that small area. So by making it small like that, we've also allowed ourselves to choose just a single A vector, which is pretty good, because if we actually had, for instance, a surface like this that's really curved, that might be too big, because right here the area vector would point that way, right here it would point that way, and right here it would point that way. So that one would be too big, so maybe we'd come back and do it like this. Now with that little rectangle, it looks a little better. So that's what we're going to do. We're going to keep choosing smaller and smaller little rectangles until both the velocity vector is constant over the whole rectangle and the area vector is constant over the whole rectangle. Once we have that, then we can say that the flux is going to be, it's got to be E dot, in this case we're talking about electric field, that's going to be playing the role of the velocity. And then the area vector, since we're dicing it up into small segments, we're going to call that dA. But when we have, a complex surface like, let's say this, okay, we're going to have a lot of different little rectangles that go around. So we need to dice it up really, really small. And each one of those little rectangles will give us a dot or E dot dA, which will give us a measure of how parallel E is to the area vector. But we'll need the contributions from every little rectangle. So we'll have to sum up all of these. And of course, when we sum an infinite number like this, that's called an integral. So that's the actual formula for the flux. Now, if you have just a single vector and you want to know what the flux is through a particular single area, then really all you have to do is take the magnitude of the area, multiply it by the magnitude of the single vector, and then multiply that by the cosine of the angles between those two vectors if they're tail to tail. In many cases, that's just a single vector. You don't have to sum them all up, so it just become E dot A or EA cosine theta. But in our case, we're going to go further and we're going to actually use this idea of flux to figure out what it's supposed to be equal to, and then we're going to apply it. Okay. So does everybody have some idea what I mean by flux? A flux is a way of keeping track of, let's say, what fraction of the velocity of each piece of trash is going exactly parallel to the A vector and therefore will completely make it in the dump truck. Does that make sense to you folks? I know, again, it's a made up construct, but as long as you understand it, that's okay. All right. Now that we had that, I'm going to compute what's called a surface integral. Now, this is advanced calculus stuff that, I've never actually been to a calculus class that got this far before. It's normally Calc 3. It's normally very late in Calc 3. You will find it in your book, in your calculus book, if you still have that textbook. It's basically analytic geometry type stuff. But in that, we'll do higher dimensional advanced calculus things like integrating on a path, or integrating along a line, or integrating over a surface, all sorts of stuff like that. So we're actually, again, learning some more math that we were never exposed to in our math classes, but we're going to learn it in physics. Okay. So what I'm going to do is I'm going to compute the flux going through a very specific shape. I'm specifically going to say I'm going to take a spherical shape and make that my surface. And I'm going to enclose inside of that a single point charge at the center of the sphere. So let me show you what I mean by that. I'm going to draw my coordinate axes right here, right here, like that. Okay. So this axis right here is going to be my x-axis. This axis right here is going to be my y-axis. So my y-axis is left and right on the paper, and then my z-axis is up and down on the paper. Now, what I'm going to do, as I said before, is I'm going to put a point charge at the origin, and that point charge is going to have a value positive q. Okay, so there's my point charge. Now I am going to construct a sphere centered on this particular point particle. And I'm trying to make it look fairly good. So I'm trying to make sure I do it pretty well. But let's try drawing a sphere now. Okay. That's not terrible. It's not perfect, but it's not terrible either. And let's see if I can move it a little bit this way. Okay, so that's good. So that's going to be my spherical surface. And I can show it's a sphere by putting the little equator line right here and then dotting it that way. And I can also show it by doing this. So we see it's a sphere, okay? So what I would like to calculate is and in this case, the surface is closed, so I could actually put this circle right around it, uh, even though I don't have to. So when you put the circle around the integral, it's basically saying, hey, uh, this equation that has this integral in it with this circle on it is only valid if you're doing it over a closed path or a closed surface or something like that. Since this one's a surface integral, it means it's only valid over a closed surface. So that's what the circle is there for. And that's ultimately how we're going to write Gauss's law. But right now, I'm just doing it over a surface and I don't necessarily quote unquote know anything about Gauss's law. So I'll kill that circle for right now, but just trying to give you a warning of what that's like. Now, we know, according to Coulomb's law, what the electric field is created by that sphere at the origin. In fact, or excuse me, by that point particle at the origin. So according to Coulomb's law, the electric field created by that Q is Q over 4 pi epsilon naught r squared, where r is the distance you are away from the origin, because the origin's where the Q is, right? So r is literally the radius of a sphere if you end up choosing a bunch of r's that are all constant, like we did with the purple sphere there. Okay. So the fact that the magnitude of the electric field is dependent on Q, which is not changing, and it's also dependent on the constant 4, the constant pi, and the constant epsilon 0. They're not changing. And then finally, it's also dependent on the square of the distance you are away from the origin. That tells me that this r is going to be a constant all over this entire surface. And that's a good thing, because it turns out that when you have an electric field that's a constant over the surface integral can be done quite easily. So that's what we're going to try to do. Now, in order to make this electric field an actual vector, then I could introduce a vector called the r hat vector. And the r hat vector is a vector that points radially outward. So if you imagine any point in space, and imagine it having an XYZ coordinate system like I've got drawn here, if you just take any point in space and then draw a line from the origin to that point in space, then that line in that direction is exactly parallel to r hat. But as you can tell, it's called r hat. So the hat means it has a unit magnitude, and that just means a unit 1, not 1 meter, not 1 Newton per Coulomb or anything like that, just 1. So that's what our r hat vector is. And it's technically the unit vector for the spherical coordinates. Just like we have an I hat, that's the unit vector for the x-axis, the j hat's a unit vector for the y-axis, and the k hat is a unit vector for the z-axis. We don't necessarily have axes like that, but we still have a unit vector in the r direction called r hat. We still have a unit vector. This is going to sound like polar for a second here, but it's called theta hat that points in the positive theta direction. And then we have another unit vector called phi hat, which points in the positive or in the direction of increasing phi, which is a polar angle that comes down from the z-axis to the point. So that point, you know, that I'm talking about in three-dimensional space can be given a coordinate parenthesis x comma y comma z. But now I'm saying it could also be given a coordinate that's parenthesis r comma theta comma phi, close parenthesis. And these are the unit vectors for that. You don't have to know these coordinate systems at this point in physics, but being familiar with them allows us to talk about vectors really easily and point to them so that everybody can agree exactly what direction these electric fields, magnetic fields are pointing. So remember, the r hat vector points always as if it shot from the origin and went through the point at which the r hat vector is located. So it points radially outward like that. All right. Now that we have that in mind, then we can say that the electric field caused by the point particle at the origin is E vector equals Q over 4 pi epsilon naught times R hat. So remember, because R hat is a unit vector, when I multiply that by E, I don't change the magnitude at all. It's literally multiplying by 1 with a vector shape, vector direction on it. Okay? So that's what the actual vector electric field will be at every particular point. And in fact, you can go a little further and choose a very specific point, and I could show you what the actual spherical coordinate would be for actually finding that differential area element, just so you'll have an idea of what's really going on with this integral. Because it turns out when we use it the way we do in this class, we use it in such a way that we don't have to do an integral. If you're doing an integral on the left-hand side of Gauss's law, you've screwed something up. Okay, it's not supposed to be an integral. It's technically an integral that you're getting out, but you don't have to do any integration to do it. You just know it's always going to be electric field times an area, maybe more than one term that's electric field times an area, but any other terms would be 0. Okay, so that's the way Gauss's law is going to work, and I'm just in the process of showing that to you. So what we could do, for instance, I'm going to try to choose another color that stands out pretty good. I think I'll use green. So what we can do is we can imagine coming from the origin a distance r like this. Notice I didn't go all the way out to the radius of the sphere, whose radius I'm going to say is little r. But the main thing I'm talking about here is this green line allows me to determine what an angle theta is. So this is the theta angle that you're probably used to from polar coordinates. And then you actually have to go up from that XY plane position. This little green line there, its length is going to be called just plain rho. But now we're going to go up a distance, say z, right about there. And that's going to be our point. And that point is going to be called r theta phi. Now, at this point, I'm going to draw a line from the origin to that data point, or to that point in space. And this distance is going to be called r. So I'll just put it right here. That is r. Okay. Everybody see what we got there? Now, in addition to that, this angle right here measured down from the positive z-axis is that angle phi I told you about, phi. Okay. What you can see from this, just looking at it, is you can see rho is supposed to be basically r times the sine of phi. And then, of course, you can from that figure out that x is equal to rho cosine theta and y is equal to rho sine theta. So that gives us that x is equal to r sine theta cosine theta, and y is equal to r. Oh, that was supposed to be sine phi cosine theta. Sorry about that. Let's fix that real quick for a, and I'll put it in the opposite order. I'm going to say r cosine theta sine phi, and this is going to be r sine theta sine phi. And then finally, you can also see that z is going to be r cosine phi. And I do sometimes call phi and phi by mistake. So it's actually supposed to be phi, but be prepared because I'm used to calling it phi my whole life. All right, so that's how the actual coordinates work with spherical coordinates. It's not that much of a stretch to learn them, but I just wanted you to have some familiarity with what we're talking about. You should be able to look at this figure, at least up close, and make sense of why these formulas are what it is. When you do that, though, you're actually able to see that r hat vector is right there. And the theta hat vector actually doesn't have any z component, but it is at a 90-degree angle to r hat and to phi hat. So this is theta hat right there. And then in the downward direction like this is, that is phi hat. Okay, so sometimes these various vectors come in handy. If you can ever picture them, then you're way ahead of the game when I go to use them. So by all means, take some time to try to draw this. Google spherical coordinates and Google cylindrical coordinates and learn as much about it as you can. It's not going to be a prerequisite for the course, but it'll make your life a lot easier and a lot easier in all your classes, because the more you start thinking in 3 dimensions, the better off you'll get in seeing 3 dimensions, and the better off you'll be able to navigate and thinking about, you know, what's in front of what's behind what's on this plane or what's higher than that sort of thing. So I'm just going to tell you, Google cylindrical and spherical coordinates. Wolfram has a good page on everything mathematical, for that matter, WOLFRAM. So feel free to check that out. But now that we have that, I can go ahead and use this diagram to calculate what the actual electric flux is. So what I'm going to do is I'm going to make a copy of this. And I'm going to say paste down here because I wanted it. Okay. But really what I need is I need to, actually, I'm going to erase this now, but I'm going to go ahead and erase all that coordinate stuff I just did, because I really don't need that now. And this was just for an explanation, and we still have the photo and everything like that there. So I think I can erase all the drawings on there and then reuse it. We'll see in a second, though. But you still got the video, so even if it doesn't, it's not a big deal. So we're going to take this surface, and now what we have to do is integrate over that surface. That's what a surface integral is. And we're also going to learn later on a line integral, and a line integral is an integral taken along a very specific path. To make the line integral into a line integral, and to make the surface integral into a surface integral, what you have to do is take the integrand and make it evaluate it actually on that line or on that surface. So that's the key to all of this. Now I'm going to see if my paste still works. Yeah, there you go. So we still have that. I can make use of that. We can see everything about the coordinates, but I'll just put it down there at the bottom. So now what I'm going to do is I'm going to imagine just a little point on the sphere. So let's say we have a point on the sphere right here. So this is an itty-bitty rectangle on the surface of the sphere, and our intent is to use that as a differential area element. And if you're familiar with spherical coordinates, this will be exactly obvious, and you'll recognize it as exactly one of the differential area elements that we use in spherical coordinates. If you're not familiar with spherical coordinates, that's okay. Really what matters is me making sense of it. So that's really the differential area element we would choose. And then with that differential area element, we would choose a area vector to represent it. And that area vector is dA right there. Now I can tell you exactly what that is if we're really using spherical coordinates. But again, you're never, ever, 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 ever going to use it in Gauss's law the way we're using it. So it's not a big deal. I just want you to have some idea of what's going on so that you can feel more confident in applying it. So it turns out that this left and right side of that, that is actually an arc of radius r, r being the cylindrical coordinate, and it goes through an angle from phi to phi plus d phi. So the actual angle is d phi. So we can say that the differential area element has a height given by r d phi, because that's what the left and right hand side is. Now, the top and bottom is actually r, but it's really turns on the radius of rho, not on the radius of r. And remember, rho is r sine phi. So in this case, we're going to have to say sine phi r squared d theta. So the r times the sine of phi gives us rho, and then rho times d theta gives us the bottom and top side. So that's actually what this is. And it also, of course, is a vector. So that means it has to point in the r hat direction. Now, that's technically what it is if you chose to do it with a double integral, which is obviously you'd have to do that because you see two differentials there. But again, we're not going to have to do that. So watch what I do for that. I'm going to now say the total flux. Oops, starting in blue again. The total flux is equal to the integral of Q over 4 pi epsilon naught. And here's my first step in making the integrand take place on the surface of that we're trying to integrate on. So remember, I told you the radius of the sphere is going to be lowercase r. So by me substituting that specific r in for the r in this formula, then I have locked at least that specific variable to keeping us on the sphere. So this r matches this r, and that's part of making this a surface integral. Now, we also, of course, have to have the unit vector, so the r hat's going to be there, and then the dA, which, remember, I went through all the details telling you what this dA could be, and it could be other things too, by the way. But look at what we're actually going to call it. We're just going to call it dA in the r hat direction, because we're not going to need to do any integration. Okay, so that's what I'm trying to show you here. Now, the dot product, like the cross product, are what we call linear operators. What that means is sort of like, you imagine, remember when we learned about functions, f of x and stuff like that? Imagine if you replaced f of x with f of c times x1 plus d times x2. If f is a linear function, that means that that'd be the same thing as c times f of x1 plus d times f of x2. So that's what I mean when I'm saying the dot product is a linear operator. It can take the parts that aren't vectors and just pull those out in front, and then just let the dot product act on the vectors themselves. So the next line of this calculation becomes, for starters, since Q, 4 pi, epsilon naught, and R are all constant, I can actually put them out in front of the integral. Okay, and the dA, because the operator, the dot product, is a linear operator, I can put that in front of the dot product as well. And then all I have left is r hat taking a dot product with r hat, like that. Now remember the formula for dot products, specifically A dot B equals the magnitude of A times the magnitude of B times the cosine of the angle between them. So if we're looking at r hat, the magnitude of r hat is 1. The magnitude of the second r hat is also 1. And r hat are identical, so the angle between them is 0. So it's going to be times cosine 0 degrees. And of course, the cosine of 0 times 1 is 1. Okay. So it turns out that what we get, after computing this integral is q over 4 pi epsilon naught times the integral of dA over the sphere. Now, it's been over the sphere the whole time. I just hadn't had time, or I hadn't taken time to write down that at the bottom, but that's what it was. It was the integral over the spherical surface, right? So the fact that we were integrating over a spherical surface and we've gotten rid of all the complications except for integral of dA, then we know the answer to the integral of dA is just A, the area. So what is the surface area of a sphere? Well, we actually happen to know that. You will know it soon too. I've got it committed to memory and have for a long time. So you're going to have it committed to memory too. Oh, I left off a squared on that R and I left off a squared on that R. So I'm going to now say Q over 4 pi epsilon naught R squared. Now remember that R squared is in fact exactly the radius of the purple sphere. And of course, the integral of dA is A, the area, and the area, surface area specifically, of a sphere is 4 times pi times the radius squared. So you can immediately see that the 4 and the pi cancel each other out, and also that the R squared cancels itself out with R squared, and we're left with Q over epsilon naught. So what we've done is did what I call a pseudo derivation of Gauss's law. I've calculated the flux over a closed surface, and the result turned out to be the charge enclosed within the surface divided by epsilon naught. So this implies Gauss's law. That's Gauss apostrophe S. Gauss's law is the closed integral of E dot dA is equal to Q enclosed over epsilon naught. So this is Gauss's law in the integral form that we're going to be using it. Okay. Now, here's the weird part. That equation looks like some equation that you've probably never seen before. Okay. It's ugly. It's got an integral. The integral's got a weird symbol on it. It's got a dot product in the integral. Oh my gosh, how much worse could it possibly be? Right. Well, the good news is it's really is nasty, but the way we use it is really weird. This is an integral equation, and we're going to, by smart hypothesis, we're going to hypothesize the form of the electric field, E, based on our knowledge of working with Coulomb's law and doing brute force integrations. We can choose from that a form for the electric field. When we have that form for the electric field, we can also use that to help us pick out a equipotential surface like we did in our second lab. Remember electric fields mapping? When we did that lab, what we did was found a bunch of equipotential surfaces, and then we remembered that the electric field would always point in the perpendicular direction to an equipotential surface or line. So the conductors were all, of course, equipotentials. So the electric field would leave the conductor surface perpendicular to the surface, and then it would have to hit each equipotential line perpendicular to that line, and then collide with the other conductor at a perpendicular angle as well. Okay. So we now have to do the same thing with Gauss's law. We're going to try to picture a surface that's an equipotential surface, specifically because we know what variables the electric field depends on. Like in the case of an electric field around a spherical charge, or even or especially a point charge, we know that the electric field depends pretty much on only the distance from the center of the spherical charge. So it depends only on R. That would mean that the electric field would be a constant if you kept the R a constant. So when you think of R constant, you should be thinking, oh, radius is a constant. That means this is a sphere. So yes, a spherical Gaussian surface centered on the spherical charge will be an equal potential surface because the electric field is going to be a constant on it and in fact perpendicular to it. Okay, so that's how we're going to use Gauss's law. So this left-hand side, because we're so wise with our hypothesis and so wise with our Gaussian surface that we choose, the left-hand side is going to turn into just E times A. Okay. Now, sometimes it'll have 3 terms or something like that. If that's the case, then you'll often get like E times A plus E times A plus 0. Or you might get 0 plus E times A plus 0. But the left-hand side is always going to be something really simple like 0 or E times A, or a sum of those. So write that down somewhere to keep your mind on it. The hard part of Gauss's law is actually in applying the right-hand side. So the Q enclosed over epsilon naught, that right-hand side can get quite nasty. And the reason to some extent why is this. Q enclosed or whatever, has to be equal to either the integral of the lambda times dl, which is a linear charge density, or it's going to be the integral of the surface charge density times dA, or it's going to be the integral of the volume charge density rho dV. Now, if I tell you something like uniformly distributed charge, then lambda r sigma r rho is a constant. So that's how we're going to work that out. Now, rho doesn't have to be a constant. I've done Gauss's law problems I've assigned to students in tests where lambda is some constant times r squared. In principle, I could make a sigma of some constant times the square root of x squared plus y squared. All sorts of weird stuff. That would actually take a double integral, but still, the point is it can be quite complicated. So it turns out this weird use of Gauss's law, which remember, I did say it's Gauss's law. It's not Gauss's helpful hint that sometimes works. It's Gauss's law, so it always works. But the weird thing we're trying to do with it is extract the electric field magnitude out of the integrand. That's a weird process we're going to do. And we can only do that with very specific symmetries. So the symmetries have to be an infinitely large plane or an infinitely long cylinder. Now, the good news is the cylinder could have a finite radius or it can be infinitesimally thin. So it has to be an infinitely long wire, for instance, or an infinitely long cylinder. Again, you know what infinitely long means in the physics world. Basically, if you're 1 meter away from the object, as long as the ends are at least 10 meters away from you, you're probably going to find some way that it works mathematically to treat it like it's infinite. Okay, so infinite cylinder, infinite plane, and then the third shape is just sphere. If you have something that's spherically symmetric, you can do that as well. So that's the 3 symmetries that work, and I'm going to show you those. And when you see those, then you can just say, okay, that's the shape, that's the Gauss's law I'm going to use every time. So here we go. Let's start off with a infinitely large surface. So I'm going to picture here an infinitely large surface like this. And clearly it's not really truly infinite, but that's okay. This is going to be my coordinate system. This is going to be X. This is going to be Y. This is going to be Z. And what I'm going to do is suggest that this goes on for infinity that way, and this goes on for infinity that way. This goes on for infinity this way, and this goes on for infinity this way. And that's enough for us to claim it's infinitely far. Now, what I also want to do is figure out exactly what the electric field strength is right here, a distance Z above. So E equals question mark. That's the problem that we're trying to solve. Okay. So what is the electric field? A distance Z above a uniformly charged infinite plate. Assume we know sigma. So sigma's a known and Z is a known, and we're asked to find the electric field some distance Z above an infinite plane who has a uniform charge density, surface charge density of sigma. Remember, sigma is something that should be measured basically in coulombs per square meter or something like that. So what I'm going to do is I'm going to think a little bit about the charges. So if I looked at the individual charges that lie along the y-axis uh, across the origin, then what you'd see is I'd have a little charge here, a little charge here, and then a little charge here. And what we'd be looking at is this is the z-axis, and this is the positive y-axis, and this is the negative y-axis. So if we looked up here to a distance z, say, we'd see that the electric field caused by this charge would point that way. The electric field caused by this charge would point this way, and the electric field by this charge would point that way. Again, assuming that it's a positive charge, and of course the electric field goes in the direction that a positive charge would be compelled to move. So if the positive charge was up here somewhere, in this area somewhere, then that's the direction the electric field would be pushing in those three cases. And what's important to see here is notice that the middle one points straight up. The right one points up and to the left, but the left one points up and to the right. So they both have y components. So you can look at it like this. This force is, that's part of it, the y component. This is the y component for that electric field. Then we have over here a negative y component. Excuse me, that's actually a z component. I didn't mean to say a y component. The blue is a z component. The red is a y component, and it's negative on the right. Whereas on the left over here, the y component is actually positive. And what that tells you is from the symmetry of it, there's going to be exactly as many electric field components pointing in the negative y direction as there is in the positive y direction. So this electric field should not have any y component whatsoever. Okay. Now, if you consider the same thing again, but this time you consider a charge in front of the origin on the positive x-axis, and then a charge in the behind the origin on the negative x-axis, you'll see that the same quandary occurs. So you're basically going to get a electric field pointing this way, electric field pointing this way, and of course these electric fields have y component, or excuse me, z components like that, but they also have x components in this case like that, and x component like that, which again cancel out. So by symmetry, we can see that the electric field should probably just point straight up. And it looks like it shouldn't depend on x or y just because of the symmetry of it. So I'm going to say, here's my hypothesis. And first off, I'll start with solution. We're going to use the closed integral of E dot dA is equal to Q enclosed over epsilon naught. And my hypothesis is E, the electric field, is going to be a piecewise function, because you probably haven't considered the fact that we're going to have an electric field for z greater than 0 and a different but similar electric field for z less than 0. So what I'm going to say is for z greater than 0, it's going to point up. So the electric field would be some E of z, meaning like I said, I argued that I don't think it's going to depend on x or y, but just z. And I also told you that I suspected it's going to point straight up. So I'll say in the k hat direction, and this is for z greater than 0. Now, for the other part, I'm just going to put a negative in front of it, sort of the same E of z. In fact, it's exactly the same E of z, but the negative is just to turn that k hat the other direction, because when you're below the plane, it's still a positive plane. So if you're a positive particle, you're going to be pushed down. And this is for z less than 0. So there's my hypothesis. So how do I go about doing this? Well, now I have to guess a Gaussian surface. So the Gaussian surface I'm going to choose is I need a surface that really is an equipotential surface, but specifically it's going to have the electric field perpendicular to it, which I don't find that helpful to think about. But when I think about what makes the electric field constant on it, that helps me. They're both true, and they both have to be true at the same time. The electric field has to be perpendicular to an equipotential surface, and on the equipotential surface, the electric field has to be a constant. So those two things are not separable. So that's something you can use. And what I'm going to say now is, because of this, I see that my E of z only depends on z. So if I set the z to a constant, I should have a constant magnitude. And of course, the electric field should point straight up. So perpendicular straight up is horizontal. So again, I'm going to choose a horizontal plane going through z. So my Gaussian surface, oddly enough, is going to be a circle whose height is z, but it's going to go down below as well. So there's my top of my Gaussian surface. And then my Gaussian surface runs all the way down and hits the plane. Now you should be able to see this part, right? But then it goes through the plane, and now we can see it again. Like this. Okay. So this part up here is also at z. So what we're going to get here is, if I look up here, I have to have a differential area element. That dA is going to be just dA k hat. Down here, this dA is going to equal negative dA k hat. Okay. Now, if we look at a little patch right here on the soup label of this soup can looking thing, I'm sort of drawing it like we do with the typical coordinate systems in case any of you are familiar with the coordinates or want to be more familiar and want to play with it. This vector right here is dA soup label. So I'll put a SL on it. That dA soup label is just going to be dA. And then I'm going to say, let's call it rho hat. Because remember we talked about rho earlier in spherical coordinates. Rho was this little guy down here. So if you imagined a vector that pointed straight out from rho, that would be exactly the direction we need. So that's what I'm actually saying here is this, boy, it's hard to read now. This dA is going to point in the rho hat direction. Let me clean that up just a little bit. It's kind of hard to read, but I'm going to say dA rho hat. And all that is just like the r hat vector, only instead of it having an I hat component, a j hat component, and a k hat component, it can only have I hat and j hat components. So there's no k hat component in it. It also happens to be the r hat for polar coordinates. So if you're talking about 2 dimensions, it would be the r hat vector for polar coordinates as well. And you might want to call it r in that way case. In fact, this is only like the 3rd time I've used rho for it. Okay. Now we've got, we still got about 13, 14 minutes, so we should be good to go. Now what I'm going to do is I have a actual hypothesis electric field. I know how to calculate the flux, so I'm going to go about doing it like this. The closed integral of E dot dA is going to have to be the integral of E of Z k hat dot dA k hat for the top plus the integral negative E of Z. Notice there is a negative in there. Actually, I should probably write that a little better. So plus integral negative E of Z k hat dotted with negative, I'll put parentheses around it. There we go again. Negative dA k hat, close parenthesis. Now that one's over the bottom, so I'll just write BOT, and then plus the integral over plus or minus E of Z k hat dot dA rho hat. Okay, and this is over the soup label, so I usually just put a SL by it. Everybody see that's a plus or minus E of Z k hat times dA rho hat. Let's say dA rho hat like that. Okay. So again, we're going to make use of the dot products being linear operators, and we're going to ultimately get like nothing. It's going to be really super easy, and that's the key to understanding this. Once you've seen all these details, you're not going to put all these details. You'll just maybe take 2 steps and show me a couple integrals went to 0, and that's it. And that's great. So we're going to write it down. I'm going to get the, since we're doing E of Z and Z is a constant on the top, that means the E of Z can come out in front. I'm going to say E of Z times the integral of dA k hat dot k hat, which we just learned that r hat dot r hat is 1. So sure enough, this is going to be 1 as well. Then we're going to see, notice the minus and the minus that we had here. We had a minus there and we had a minus there. So when we multiply those two, we're going to get a positive. I can pull the E of Z out again, and I get the integral of dA k hat dot k hat, which of course is 1. And then this one's kind of nice. I clearly cannot pull the E of Z out because I have to integrate all from the very top of that soup can looking thing, or pillbox as we call it, all the way down to the very bottom. And that's why I've got plus or minus, because the electric field points up for the top half, but once you get below the plane, it points down. So I have to have the two different directions for that. So all that tells me that I can write this way. I can say plus or minus EZ E of Z dA, but then it's K hat dot rho hat. Now, remember what I told you about rho hat is it's basically like R hat, except it can't have any K components. Well, if it doesn't have any K components and you're dot producting it with K, that should tell you that the dot product should be 0. But you can also get it from the magnitude of K hat is 1, the magnitude of rho hat is 1, and then the angle between them is 90, so it's cosine 90 degrees. So all of this is equal to 0. So what we end up getting is, notice E of Z times the integral of dA just means the area. I'm going to tell you that the area of the top is just A. So this integral is going to become E of ZA plus E of ZA, which equals 2AE of Z. Okay. Now, the way I do this is a weird thing, Gauss's law. It's one of the few equations where you have to work with both sides. So I generally start this off not just writing the closed integral E dot dA. I say left hand side, and then I underline it and put a colon up there. Okay. So that was the left hand side. Now I got to do the right hand side. So the right hand side is Q enclosed over epsilon naught. Now, what we said was the actual charge per unit area on this plate, our infinite plane, was sigma. So the way lambda works is if you multiply lambda times the length, you get out the charge. The way sigma works is if you multiply sigma times the area, you get the charge. And then the way rho works is if you multiply rho times the volume, you get the total charge. So that's what we're going to do here. In this case, we're going to multiply it by the area of the top, which is just A, but that happens to be the area of the plane that's enclosed inside that Gaussian pillbox or soup can, if you want. So this is going to become just plain sigma times A, which remember happens to be the same area that we just finished calculating in those integrals, divided by epsilon naught. So now we can take these two results and we can say left hand side equals right hand side, and I don't know why I wrote a colon there instead of equals. With this, I'm going to get 2AE of Z is equal to sigma A over epsilon 0, which immediately shows you that you can get rid of the A. And guess what? The electric field E is actually going to be equal to positive sigma over 2 epsilon naught K hat for Z greater than 0, and negative sigma over 2 epsilon naught K hat for Z less than 0. Okay. In fact, if you wanted to plot that, which you actually could, that's something we often ask you to do, then this would be our electric field. This would be our variable Z. And yes. Okay. Yeah. Yeah, that's right. Okay. So sorry about that. So right here, this would be sigma over 2 epsilon naught. And then right here, this would be negative sigma over 2 epsilon naught. And when you plot this It's going to be that quantity for z greater than 0, open hole, and it's going to be that quantity for z less than 0. Okay. It turns out that having an electric field discontinuous like this only happens for a very specific reason. It turns out that you only have a discontinuity in the electric field component perpendicular to the surfaces. You only have that discontinuous when there's an actual surface charge. So not only that, the actual discontinuity, the difference between the positive one minus the negative one, is going to equal sigma over epsilon naught, because that turns out to be exactly what the difference is. So that's kind of a neat thing. Whenever you find a discontinuity in an electric field, if you calculate the difference between the high and the low, that will give you the surface charge divided by epsilon naught. Any questions on that one? Okay, so yeah, this is something that generally scares our students. Okay. The good news is, like I said, it's not as hard as it seems, because you're never actually doing the integral on the left-hand side. That being said, next time I'll show you several examples and you'll see quite a bit of integration on the other side is possible. It doesn't have to be. A lot of times you can find tricks around it so you don't have to do the integral, but sometimes you just have to. So we'll show you that next time. Right now, just know that this is something you should try to probably commit to memory. Try to watch the video over and over again to make sense of how I did it, to make sense of all the words I'm saying. Those words are actually pretty important. They're explaining key principles to you. And then see if you can, turn off the video and do the same derivation. Your book does a similar example in it, but he doesn't explain all the details, which I admit is a lot less confusing. But what I was always having troubles with when I went home after reading this stuff is I'd go home and I didn't quite understand it enough to regurgitate it. So until I figured out what was actually going on with the math, I didn't really understand it well enough to do it consistently. But finally, I figured out with the math how I was able to do it. And hopefully by me explaining the details of the math that you don't have to do. Remember that first line of integrals I did there. If you wrote those out, that would be great. But to be honest with you, you can go straight from that to 2a ez, because it's got to be a times e for the top and a times e for the bottom. That's what's supposed to be turned in. The right-hand side, that's supposed to be really easy. Sigma A over epsilon naught, set two equal to each other. Boom, you're done. So I'll show you two more, at least two more next time. And then as the chapters go on, we're going to be doing other examples that give me an opportunity to do Gauss's law again. So you guys have a good one. Make sure you chat me your first and last name if you haven't already. And you guys have a good one. And remember, you got to get your test done this week. I am allowing up to Monday, but you have to ask for that. So Sunday is the latest otherwise. And I'm not sure the office, any of the testing centers have Sundays. I think they have Saturdays, but not Sundays.
Hey, regarding that, I do think I'm gonna have to be the one of the ones that take it on either Zoom with you or lockdown browser.
Okay.
Because I have night classes this year and it's just not working out with the only time I could take it is I think the Portsmouth one is open at night, but my parents are like, no way are you gonna
I
be
don't
out
want you
there.
going to Portsmouth at night.
Yeah, my parents are thinking the same way. So I'm sorry. I think I'm gonna have to make lockdown browser or Zoom or something else work.
Yeah, that's not a problem. Just let me know. We'll work out some kind of agreement about when you can do it. I might even just announce when you're doing it, and I might get a couple of students to do it, and I could actually proctor it as well. But the main thing is definitely get your lockdown browser installed and updated, and then get Respondus Monitor as well. Make sure your computer's ready to run that, and find a mirror that you can use.
Okay, I took a summer class and I used both of those over the summer, so I'll
I thought you did.
Be on the hunt for a mirror that I could take off the wall.
Sounds good, Hannah.
Okay.
Hannah from the Eastern Shore.
Yes. Thank you.
This is Carter. Keep me posted about if you end up hosting like a you proctor it test, just because I'm gonna go to the testing center on Thursday to try to get a scheduled time, but if you end
Okay.
up putting up a scheduled time, just keep me posted.
Well, it looks like I'm going to do at least one where the student's doing it with Respondus, and I may or may not be able to proctor that, but Respondus is good enough. So if you need to, Carter, it's fine.
Okay.
Thing with the other students that talked to me earlier.
Okay, yeah, I have the same mirror I used over the summer, so
That's cool. No worries.
I think that worked last time. So, all right, cool. Thank you.
Thank you, Carter. Anybody else?
Yes, so I just want to say too that I would have to do the responders or the assume lockdown 1, 2.
What's your first name? It just says iPhone here.
Sorry, it's Evelyn Rodriguez.
Oh, okay, no problem, Evelyn. Yeah, it's not a big deal. Like I said, the big thing is you got to just keep your hands up. What I'm trying to fight with the mirror is basically we have I've had some problems where students had stuff either in their laps or written down below, and they were spending a lot of time looking downward. If I don't see you looking downward at a piece of paper that you're doing some writing on or something, then that starts to look suspicious. And basically what's going to happen is if I see something like that in the video, because they record it for me, even if I don't proctor, then I'll just have to mark it, and then you'll have to come in and take it regular, no matter whether you were actually cheating or not. It's just what I'd have to do if you act that way. So just as a warning ahead of time, make sure when you're working, don't look down and stare down for no reason. If you're looking down, it should be because you're looking down to write something. If you want to stare off into the distance, that's fine. Make sure you stare off to the distance to somewhere I can see. Because if I keep seeing you looking off to the distance behind your mirror, then I'm going to start thinking something. So it's kind of a pain in the butt to do that at all. That's why I'd much rather you guys get it proctored. But I'll do it for you. It's no big deal. Just let me know, and we'll get it set up. Texting is better than phone than email for that, by the way. Anybody else here?
Yes, I just have can you hear me?
Yes, ma'am.
Okay, so were you saying that if we're going to do it at the testing center, you needed to know our information?
Oh, no. If you wanting to take it by using a mirror and Respondus, then contact me and
Okay. All right, you said we have until Sunday, correct? For if we're doing it at the testing center, but Saturday pretty much.
Yeah, and make
Okay.
sure you find out whatever their rules are, because some of them require a day in advance, all sorts of weird stuff. And
Yeah, I think
on 90
Virginia
minutes.
Beach needs 48 hours in advance, so I need to schedule it like soon.
And like I said, if we need to, we can open up Monday as well. I'm not averse to that.
Okay. All right, thank you.
Thank you, Tanika. Anybody else? Hey, Tim.
Howdy.
What can I help you with, sir?
Let me get my phone. I took the practice test a few times today. I had some questions regarding a few.
No problem. I've got it set up where you should be able to share your screen with me now. So if you need to, that's fine.
I unfortunately took it on my phone.
Oh, okay, gotcha.
So yeah. Do you happen to have the test bank?
I could possibly find it. Yeah, if you want me to pull something up, do you have some words or exact words of the test?
Yeah. So whenever you're ready, I can read it.
Yeah, hold on. Let me go to, I'm going to go to your course because that has a different bank than my other courses.
Okay.
So now I'm going there. Now I'm going to quizzes. And what chapter do you suspect this would be, maybe?
This is definitely chapter 16.
Chapter 16? Okay. And it's a problem where you're working out with numbers, not a conceptual question, right?
Yes.
Okay. I've got chapter 16 open.
Okay. As shown in the figure, 3 charges are at corners of a rectangle.
Okay, as shown in the figure, as shown, 3 charges are at the vertices of an equilateral. As shown in the figure, 3 charges at the corners of a rectangle. That one?
Yes, that one. Yep.
Okay. I'm looking right at it. It says as shown in the figure, 3 charges are at corners of a rectangle. Let me do this real quick. Let's do this one. Okay. So what you're looking at is this problem right here.
Mm-hmm. Yep.
So it says the charge in the bottom right corner is negative 90 nanocoulombs, and all the other quantities are accurate to two significant figures. What is the magnitude of the net electrical force on Q due to the other two charges? Okay.
Yep.
So the force on here due to these two. So first thing you're going to do is you're going to have to work out the force, the magnitude of the force between these two.
Okay.
And then notice that this one's a negative charge and the Q is a negative charge. So they're going to repel. So that means the force on capital Q due to that negative 5 Newton, or excuse me, 5 nanocoulombs is downward. It points straight down. So that's just a straight vector. This other one will have to be along the line connecting these two. So you see where Q and the 15 nanocoulombs are. You're going to calculate that magnitude. And then what you have to do to figure out the X and Y components of that is you take the inverse tangent of 1 over 3, and that'll give you this itty bitty angle here. The angle between the hypotenuse and the 3 centimeters. Okay. So you can then take the cosine of that angle and multiply it by the magnitude of the 15, and that'll actually give you the X component, but you got to decide whether it's going to be positive or negative.
It should be positive, right? Because the positive 15 nanocoulombs.
So that one's positive, which means it's going to be attracting the negative charge. So the force on the capital Q will be up and to the left. So the force will actually be towards the 15 nanocoulombs.
Okay.
That means the Y component would be up and the X component would be to the left.
Okay.
Does that make sense?
Yeah. When I was like looking up Chegg for it, the person that did it just and I don't know if they assumed, but to me, based off like their picture, it looked like they assumed that the angle by the negative Q at the bottom right, they did that as 45 degrees.
Yeah, they can't do that with that one.
Okay.
Yeah, if that was 3 centimeters and 3 centimeters, that would be fine, but not with 3 centimeters and 1 centimeter.
Okay.
Let me, I'm actually drawing it on my pad right now, and I'll close off this problem.
Okay.
And work it out for you, or help you work it out.
Yeah, I would appreciate that. Chapter 16 was not my strong suit.
Yeah, vectors are tough, especially if you take a little break from them a little while.
Yeah.
So that, that tends to be a sort of taxing thing. This is negative 90 nanocoulombs. Okay, so now I'm going to stop this share and start the other share. I think I got all the numbers I need. And they want to know the magnitude of the electrical force.
Yep.
Okay.
So, right off the get-go, I know that I'm using the formula F equals K times Q1, Q2 over R squared.
Right.
I have to break up the vectors like you said earlier.
Right.
So let's see. The issue is I've been like doing these practice problems on a whiteboard. Which once I move on to the next question, I don't have enough space, so I'm gonna start doing it on paper.
Gotcha. Yeah, that's kind of a problem with that. Okay, so I wrote the question down. You should be able to see it now. Are you seeing my board?
Yes.
Okay. So yes, you're right. What we're using is F is equal to K or excuse me, did they ask for the force or did they ask for the electric field?
They asked for the force, I believe.
The net electric force. Gotcha. So let me change this. Oops, wrong color. So there I just erased that and redid it. Look at crackhead. Oh, good gosh. Okay. It's F total. Okay. So what I want to tell you is, yes, we're going to start off with F equals KQ over R squared. In this case, I'm actually going to say it's EQ over R squared, because what I'm going to do is I'm going to use the fact that E is equal to KQ over R and F is equal to Q times E. So I'm going to make use of that. I'm also going to realize that F total is going to be FQ, which is FQ, let's say 5. No, I'll put the 5 next to the Q, plus FQ 15. In other words, what I'm saying is I've got to calculate, well, I'll do the electric field. So let's go ahead and make it an E instead of an F in all these cases. So I've got to do the electric field on Q due to the -5 nanocoulomb one. And then I've got to do the electric field at Q, big Q, due to the positive 15 nanocoulomb one. And then add those two, and then that'll give me the total electric field.
Okay.
Once I have that total electric field, I just have to multiply it by the -90 nanocoulombs, and that will give me the actual force. Does that make sense?
Yes.
Okay. All right. So that wording might be worse, but you can look at the end of this video. That'll be posted tonight or first thing tomorrow. So if you need to go back and look at it, it's not a big deal. What we're going to do is, first off, we're going to say at EQ5. So EQ5 is going to be 9.0 times, I think they actually told us to just use 2 sig figs, right? Yeah, they did. So it's going to be 9.0 times 10 to the 9 Newton meters squared per coulomb squared. That's the K. Now the Q causing this is the -5 nanocoulomb. So I'm going to say 5.0 times 10 to the -9 coulombs. And then I'm going to divide that distance that by the distance squared, which is 1.0 times 10 to the -2 meters squared. So that'll give me the magnitude, and then I just have to know that it points straight down, which isn't too bad to deal with. So in this case, I'll say 9 times 10 to the, times 10 to the 9 times 5 times 10 to the -9. And then I'm going to say divided by parentheses 1 times 10 to the -2.
That's 0.01, right?
Yes, 0.01. And that gives me 4.50 times 10 to the 1, 2, 3, 4, 5. And that's newtons per coulomb. Okay. Now, that means EQ5, since they're both negative, the electric field at the point, actually, I should just do the electric field here. So the electric field at location of Q is basically, if I put a positive charge where capital Q is, that would be pulling up into straight up. So I'm going to say EQ5 is 4.50 times 10 to the 5th newtons per coulomb upward. Upward. I don't know where that Y came from when I was trying to write an R.
It's been a long day.
Yeah, exactly. So that's upward, which really means the Y component is positive. Okay.
Okay.
Now, when we multiply that by the negative 90, that means it's going to point it in the right direction for the force, because the force really would be in the downward direction on Q. But that's the whole point of this equation being F equals Q times E. That's the one where you actually use the sign in.
Okay.
Okay. That you look like you may have been looking for that equation when I pointed it out to you.
Yeah.
That is the equation that we use to define the electric field compared to what the original force equation was.
Okay.
Remember, the force was K Q1 Q2 over R squared, and I just divided one of them out. That's where it came from. Okay.
Gotcha.
Now the other force, the other electric field, well, evidently I'm gonna have to write with the actual writing pen, is EQ15, and that's 9.0 times 10 to the 9 Newton meter squared per Coulomb squared, times this time it's going to be 15 times 10 to the negative 9 coulombs, and this time it's going to be quite a bit of a distance away. Instead of 1 centimeter, it's going to be 0.010 meter squared plus 0.030 meters squared. We would take the square root of that, but then we need to go back and square it for this equation. So I'm going to skip that and just leave it as is.
Okay.
Because that actually works. So now if I do that, I'll say 9 times 10 to the 9 times 15 times 10 to the negative 9 divided by parentheses 0.01 squared plus 0.03 squared, close parentheses. This gives me 1.35 times 10 to the 5th. Yeah, that's 10 to the 5th, and that's newtons per coulomb, but that's just the magnitude. Okay. Now, to make sense of that triangle, I need to use a little trig and say tangent inverse of 1/3 is equal to, I'm going to call that angle theta. So I'm going to say shift tangent inverse parentheses. My calculator literally makes me use parentheses. If I do 1 divided by 3, it'll take the inverse tangent of 1 and then divide the answer by 3 like a crackhead. So that drives me crazy. So inverse tangent of 1 divided by 3, that gives me 18.43 degrees.
Yes.
Okay. And we could also figure out what the hypotenuse is, but I just bypassed all that, so I don't really need it. Right. So what I need to do is remember that triangle is the hypotenuse of it is the direction of the force or the electric field EQ15. It's going to be parallel to that hypotenuse. So it's a positive 15 nanocoulombs. So at the location of capital Q, the electric field should point down and to the right as a result of this one. Okay, which is I think that's the opposite of what I told you earlier because we were calculating the force then.
Yeah.
Yeah, so this is the same thing except we're calculating the electric field. So in the spot of Q where I need to know the electric field, it's the electric field is defined to be the direction a positive charge would go. So if I stuck a positive charge where that capital Q is, it would definitely go down and to the right. When I later compute the force, it's going to be it's going to flip that by multiplying by the negative 90.
Okay.
Okay. So what I'm going to do is I'm going to imagine my vector pointing this way. This is EQ15. Okay. And now I should call this y component, it's in the downward direction. So that's the actual y component, and it should be negative. But the x component is pointing to the right. So that one gets to be positive like this. Okay.
Okay.
So I can say E Q15 sub x is equal to positive 1.35. Jackson's calling showing 1.35 times 10 to the fifth newtons per coulomb. Notice I put the positive there because I need it to be a positive sign. And now I got to multiply it by cosine of 18.43 degrees. That's more than enough sig figs. So cosine, my last answer. And now I multiply that times 1.35 times 10 to the fifth. And that gives me 1.28 times 10 to the fifth newtons per coulomb is equal to E Q15X. Okay. Now E, I'm going to use the red here since that one turned out to be positive. That'll be a little reminder for me. So EQ15Y is going to be a negative 1.35 times 10 to the fifth newtons per coulomb times the sine of 18.43 degrees. That gives me a negative number, 1.35 times 10 to the fifth times cosine 18.43, close parentheses.
It should be sine, right? Not cosine.
Oh, thank you. Appreciate that. 1.35 times 10 to the fifth times sine 18.43. I was like, wow, I got the same number. That's amazing. That can't be right. So this is 4.27 times 10 to the fourth this time, newtons per coulomb, and that's EQ15Y. Okay. So we can also say that I'll use green here. I can now say that EQ5Y is actually up. So that's going to be positive 4.50 times 10 to the fifth newtons per coulomb. Okay. So now if I want the EQ sub x is just EQ 5 sub x plus EQ 15 sub x, which is EQ5x is positive 4.50 times 10 to the fifth newtons per coulomb, plus EQ15 would be plus 1.28 times 10 to the fifth newtons per coulomb. So 1.28 and 4.50 is going to be 5.78.
Sorry, I'm playing catch up right now.
Times 10 to the fifth, no problem, newtons per coulomb. Yep, that all looks good. Now we can do the same thing with EQY. The total electric field at Q in the Y direction is the electric field at Q in the Y direction due to 5, plus the electric field at Q due to 5 due to 15 in the Y direction. Of course, EQ5 had no, that was supposed to be Y before. Oops. I think I wrote it right though.
I also have a question. Where'd you get the 5.78 times 10 to the 5 from? I don't see that.
I was actually adding those two, but it looks like I might have added an X to a Y, not paying attention. So
I see the equal too.
yeah. Yeah, I did do that, by the way. So let's kill this. That part's right, but EQ5X. Nope, I got it wrong from the very get-go. Okay, so EQ5X is actually 0. So I'm going to put 0 there. Because remember, it was purely straight up and down.
Oh, yeah.
And then EQ 15x, that's actually positive 1.28 times 10 to the 5th newtons per coulomb, which gives me 1.28 times 10 to the 5th newtons per coulomb. So I have that as a magnitude for the x component. The EQY is EQ5y plus EQ15y. The EQ5y does exist. That's the 4.50 times 10 to the 5th newtons per coulomb, plus the EQ15y is the negative 4.27 times 10 to the 4th newtons per coulomb. That's actually kind of messy to do. Normally when you add them and subtract them by hand, you get them to the same power. So I'm just going to punch it out in my calculator. I'm going to say 4.5 times 10 to the 5th minus 4.27 times 10 to the 4th. And that gives me 4.07 times 10 to the 5th newtons per coulomb. And it is positive.
Okay.
Should that be positive? I did minus 4.26. Yeah, that should be positive. That's just 4 plus 2 be 6. Guess that works about right. 4.5 times the 5th. 4.27. Okay, so those are my two components of my electric field. If you want the actual magnitude of the electric field, you just have to do this Pythagorean theorem. What we have is a positive x component that's 1.28 times 10 to the 5th. And to be honest with you, since they're both times 10 to the 5th, you don't even have to include that. You can just treat it like this. You can say, all right, well, this is 1.28. And oops, that other one had to go up. So I'll do this as 1.28, and then the other one has to go up a lot. So that's 4.07. Both of those are times 10 to the 5th. So we get that the hypotenuse should be EQ magnitude, which we just call EQ, is actually equal to the square root of 4.07 squared plus 1.28 squared times 10 to the 5th newtons per coulomb. So I'm going to say 4.07 squared plus 1.28 squared. Both of this is good to the nearest whole number. Now I'm going to take the square root of that. That's the square root of 18.203. And the square root of 18.203 is 4.27. Of course, now we still have the times 10 to the 5th.
Yeah, I got 4.26 times 10 to the 5th.
Yep. Okay. So now all we need, because the problem was asking for FQ. FQ is just Q times E. Since they're asking for the magnitude, I don't even need to put the number in. But if you want the direction, you literally have to put that negative in, because the negative is what turns the directions correctly. So in this case, I'm just going to say 90 times 10 to the negative 9 coulombs times 4.27 times 10 to the 5th newtons per coulomb. And so I'm going to say times 90 times 10 to the, oops, -9. That gives me a force of 0.0383. Actually, it should be 3840.
Wait, what should be 40?
That's the magnitude.
Oh, okay.
So if I'm looking at this, let's see if this is if it has the answers here. Yes, this says 3.8 times 10 to the -2 newtons, and that's exactly what we computed.
Sick.
Fancy, huh?
Yeah, it's a lot.
Yeah,
And
I know a guy.
yeah, I haven't taken physics in like over 2 years now. So
Well, that might have seemed a little harder. I don't know. I thought I thought it was going to be easier to calculate the electric field and then just multiply by Q. Plus, that's a thing that my students always forget that they can do. So that was another reason for me doing it. But you might have gotten more out of it if we just use, instead of Coulomb's law for the electric field, if we use Coulomb's law for the electric force, it would have been K little q big Q over R squared. And then you just do the same thing, but you wouldn't have that last step of multiplying by Q. So you could try that as well, but that basically gives you the answer.
okay.
All
Cool.
right. Hopefully that helped.
Yep. And I saw some other questions. I guess I'll ask just one.
I think I have time for one more.
Okay, cool. This one is RMS speed.
So you think that was 17 maybe? Oh, wait a second.
RMS I thought was 18, right?
Yeah, there might be some 18 in there. So let's check the 18. Oops, not that one. I went to 18 for the calculus space book. We don't want that.
Yeah, and I'd prefer no calculus.
Yeah, that one. Nope. Okay. So some wording for this. Oh, another here. Oh, there it is.
The RMS speed of the molecules of a gas.
The RMS.
Yes, speed of the molecules.
There's none in there. Let's do speed of molecules. There's nothing in here either. Oh, that might be because I'm in chapter 19. That had something to do with it. There I am. What was the next word? The molecules or something?
Yeah, speed of the molecules.
Man, it's not showing that either. And this is chapter 18. Let's do some more questions and then try it. Speed of the nothing in there. Maybe it was in 17. I don't know. Definitely no questions there. Any chance, did they actually make you calculate something?
Yeah.
Okay. I'm just checking to see if it's maybe a concept question instead. Let's do 17. Nope, it's not in 17 either. I can't find it.
Okay. So,
Let me try 16 real quick, just for the heck of it, because we've done everything else.
yeah.
Hmm.
Well, it gives me, the RMS speed, that's 200 meters per second, and then it gives me a temperature at 300 Kelvin, and then it's asking me for the mass of the individual molecules.
Okay, that's not supposed to be one of the problems that's coming up on yours at all, I thought. But the formula that you're using here is, let me show you. What you use for this problem is 3/2 KT is equal to 1/2 mv squared. So you can see that the 2 and the 1/2 cancel out, and you get from that, of course, that the velocity is equal to the square root of 3 KT over m. And the T has to be in Kelvin.
Okay.
But now you can just, since you were actually asking for the molecule's mass, you could just take that equation and solve for m instead. But I really didn't think we even put that in this test, so you shouldn't see that on the test when you take it.
Okay. Yeah, because I was looking through the formula sheet, and I didn't see anything.
Yes, some time ago, something got mixed up where I had some questions from a different book, and they covered that in a different chapter, and I think that might have been where that came from. Did you just get that today?
Yeah. It was under practice test 3.
Oh God, that's crazy. All right, I have to check my bank again because that shouldn't be having stuff like that. But yeah, so you understand how to do it now?
Yeah, I had the formula, which is better than not
Yeah,
having.
exactly. That would help. Now there is some reason for that to pop up in a textbook like this, because you're in the second semester, so they could use that to do some calculation related to stuff we're doing today. So they expect you to know it because you supposedly already had it, but still, I did not assign that to you, and I won't be putting something like that on the test. Okay.
Okay.
All right. Well, I got to split, man. Is there anything else I can help you with quickly before I go?
No, I'm all good. So I
Right.
do appreciate your extra time today.
No problem. I hope it helped. You have a good one.
Yep, you too. Bye.
See you, Tim. Bye-bye. Bye-bye, everybody. Bye-bye.